We're now going to start our coverage of Spring WebFlux. If you recall, much earlier in the semester, probably week 2 or 3, we talked about WebMVC. WebMVC was this servlet stack that used synchronous blocking I/O. Now we're going to talk about Spring WebFlux, which, as you can see here, is non-blocking and asynchronous and uses reactive types all over the place, while allowing communication to take place across processor boundaries or process boundaries and network boundaries. So Spring WebFlux is a non-blocking web framework that ideally leverages multiple cores more effectively than the traditional old school way of doing Spring WebMVC. And therefore, you can handle a very large number of concurrent connections to communicate across networks or across process boundaries on the same machine without running into some of the deficiencies of old school Spring WebMVC. This is, by old school, I mean things prior to the introduction of virtual threads. In this model, requests are handled in an asynchronous and entirely lazy model and lazy manner, so nothing blocks. This is actually quite interesting. So let's say we want to query some airline reservation system to find what flights might be available from one city to the next. And you can see here that we call find flights. We get a flux back, which does not block. This will come right back. Find flights, return another flux. That doesn't block, comes right back. Find flights, get another flux back. That doesn't block. And so as a consequence, the finding of the flights, which is taking place over here on the server side with a little guy running around, that might take a while, but the threads servicing the request and response don't need to block. They can come right back to the caller, and the caller can do other stuff like invoke other operations or handle the user interface or other touch events or whatnot, while the asynchronous computations are running on the server side. One of the nice things about this is you don't need a large number of threads. You typically need about as many threads as there are numbers of processor cores, which is a win. Now, you may have to use thread pools such as the bounded elastic thread pool if you're going to be blocking, which you probably are, but that's okay because that's baked into the underlying Project Reactor framework. So we're going to use all the Project Reactor stuff that can handle different types of thread pools, but we're going to extend its reach by using this WebFlux mechanism so we can send and receive reactive types like fluxes and monos across the network boundary. Something else that's very important here in this type of a model is the need for support for back pressure, non-blocking back pressure. We've talked about this many times. If you have someone generating events, some fast publisher that's generating events faster than a slower subscriber can keep up, then back pressure may be needed. And one of the cool things is that WebFlux supports back pressure that goes across the network boundaries. So it's all kind of baked into the programming model, so it looks fairly seamless from the end user's perspective or the program's perspective. Now, Java 19 and beyond support virtual threads, which can give you very much the same benefits without having to use non-blocking clients and servers. So your mileage may vary, but you can decide which one you like. You will have had experience with all these things by the time we're done with the class. And you can decide whether you like the asynchronous programming model with Project Reactor or and WebFlux, or the more traditional synchronous interaction model with classic Java types and Spring WebMVC when combined with virtual threads. And I should also hasten to add that the latest versions of Spring, I think we're probably on Spring 7 by now, supports all this stuff seamlessly. In fact, Spring 7 supports very modern Java features natively, like the latest and greatest versions of virtual threads and other features that are available in Java. The communication that takes place between senders and receivers, or clients and servers, or publishers and subscribers, whatever you want to call them, uses the Project Reactor reactive type. So you can pass fluxes and monos back and forth between clients and servers. As you know, as you recall, you can have fluxes where you have a single return result, which might or might not contain a value. And then you can also have fluxes that may or may not return values, but if they do, they can be from 0 to infinity. And as you'll see here, here's an example where we might want to call a currency exchange rate service, which will return the exchange rate of two currencies, say pounds to yen or whatnot, and that returns a mono. And we might also have another method called find departure dates that's going to take a departure airport and arrival airport and then return a list, a flux of departure dates based on those airports. And of course, there's the typical set of operators from the reactive X API that you can use here to program on the client and server. Now, here's where things get really interesting. This is the main motivation for using this approach. And I think I should probably mention that this is cool even if you use Java virtual thread. So even if you decide to use the Java virtual thread model to stick with the synchronous style of communication, what we're about to talk about is still cool relative to that approach. So what you can do with reactive flux types is they can be streamed element by element, which makes your clients more responsive. And that is in contrast to using classic Java types like lists or arrays, because lists and arrays have to buffer everything up on the server side before they're sent back in one fell swoop back to the client. So that's one of the major differences. Even if you're using virtual threads, that still is an issue you have to be aware of. So what you can do is you can stream the results back from the server to the client, so the client can start processing the results before everything is finished. And you don't have to buffer everything up in one big giant list or array. You can send them back in dribs and drabs as the computations complete on the server side, and those values are emitted using the reactive types. Oddly enough, and this is a real disappointment, Android doesn't support WebFlux reactive clients for whatever reason. So it's disappointing. We tried quite a bit to get this to work, never could get it to work. So it doesn't get you quite as much as you'd like if you're running on Android, but if you're running on other platforms, then you can get that fully streamed asynchronous communication from stem to stern. Also, oddly enough, Spring 6, now Spring 7, HTTP interface doesn't work on Android either, which is also a disappointment. Something else you can do, and we'll talk about this and probably show some examples, is you can actually have what are called streams. And so in this particular case, this is really meant for communication that could run for an indefinitely long period of time, like a media player of some kind. This example is a little bit hokey, but it illustrates the point. So if you give yourself an annotation that says, I am going to have the media type of text event stream value, then the client essentially has an open connection, using that word loosely, to the server. And so it'll keep streaming back the exchange rates. So as you can imagine, exchange rates are going to change over time. And so this will be able to tell you as the exchange rates fluctuate, and you can get results back that indicate what the latest rates are. You could also imagine using something like this for something along the lines of a stock ticker program where you can get the latest quotes, and you just kind of keep it open and you can stream back the results indefinitely. Back in the day when this technology first came out, there were a lot of experiments that were done comparing and contrasting the use of the traditional Spring WebMVC servlet stack with the modern Spring WebFlux reactive stack. And they found that you were able to get better response time, and the number of requests per second were higher because of the use of asynchrony. I'd love to see what happens if people rerun those experiments now with virtual threads. You will probably get similar performance, but keep in mind the difference between WebFlux, where you can stream the results back through fluxes, whereas with virtual threads, you're typically not streaming stuff back. You're consolidating it all in a big buffer on the server side and then sending it back in one chunk, which could have latency and memory management or memory utilization impacts. So that's the end of the overview of Spring WebFlux.